Okay, we will continue with where we left off the other day, which is just before the introduction to the perceptron and the perceptron learning rule. Now, before I move on to the topic, I just want to check with you. Are there any questions that you may have for me? That there's some parts maybe it's not very clear, or you want to seek further clarifications. If not, just a kind reminder, the following students are RMH 4 and RE4. Please check if you have correctly uploaded your lab report to the Google form, because there is no record of your submission in the system. It will be very good of you, highly appreciated, if you can submit your report by tomorrow 5 p.m. so that I can complete the marking of the lab reports. Thank you. Now, if you're not here, can your friends of these 3 students, please alert them, inform them, because maybe they submitted and then the report got lost. But so kindly just resubmit the form, the lab report, so that I can complete the marking. So we will continue with the and go into the perceptron and the perceptron learning rule. Let me just bring up the relevant slides on this. Okay, a minute. Okay, get it up. So I think just before we stop, last 2 days ago, we talked about some of the pioneers, some of the major contributors, some of the major researchers who actually contributed to the field. I can see it's a very quite an established field. The contributions are from various people, right? And I think ranging from some of those actually help, and some of those actually have do not believe in it. And also I can see not only the Westerners who have contributed, but also Asians, notably Professor Sunichi Amari and Professor Kunihiko Fukushima, among others. Maybe in the near future, some of you your names will be there, as a major contributor to the field. So let's look at the perceptron. What is it, and then what it can do, or and also what it cannot do. What are its limits to its capabilities? Now, the perceptron, actually, we have started doing this this week in the last lab practical to study to actually build and study the simple perceptron. Now, the perceptron is the simplest form of a neural network. So basically, it is a single neuron with adjustable synaptic weights. Remember, the synapses are actually the weights. So we're actually reminding you that it's actually the synaptic weights, which is actually copied, if you like, right? Copied and also modeled from the actual biological neural network. Now, the perceptron normally uses a hard limiter, which is basically a step function, or you can also call it a sign function as its activation or transfer function. So this is basically a single neuron, and this is the simplest of all the neural networks you can find. Just one neuron, right? And it's very simple. Now, the weighted sum of the inputs. So if you can remember, basically we sum up all the inputs. That is the function of your single neuron. So the weighted sum, the inputs are not just connected straight to the processor. It's actually weighted. There are some weights attached to each of them. And I think some of you actually started to explore, to develop the perceptron, was surprised to find that your results that you get in terms of the convergence map, the convergence itself of the ability of the perceptron to learn was not similar to the what the the lab manual shows, right? And then in that case, the network wasn't able to converge. Although it converges and stabilizes, but it wasn't the same shape as the one shown in the lab manual. Do not despair, do not worry, because as if you look at it carefully, what can you see? You can see that for a brand new neural network, right? You know you have the inputs. You know what the input should be, and you know what the outputs should be. So those are defined. Now, what about the weights? The weights that is coming to the weights coming to the that is will modify your inputs. The weights which modify the inputs, this one is unknown, right? So you don't have a values for this. So this ones here you have, and this one you have. So this is a perceptron. So what about the circles shown here in blue, the weights? What value should they be? So therefore, as some of you may have guessed, right, the weights have to be initialized randomly on top of that. That's why you look at it. That's why we spent some time in the lab number 2, practical number 2, whereby you study the different random functions, random generators. So in the random generators, you find that that's how because many of these systems here, you have to initially randomize it because the settings are not known, so you have to start from somewhere. But the good thing is that even though you start from anywhere, most of the time, it will converge. Unlike because why do I say most of the time? Because in some cases, the network will not converge to what you want. It will not learn the function because the parameters are not set correctly. For example, you learn too fast. You set the learning speed too fast. So as a result, it jumps, right? So it jumps and then it skips, and then as a result, it was not able to learn. So that is the few cases whereby it's not. But of course, if you tune it nicely, you're able to tune it with the right values. It should learn all the time, right? Of course, also there's also the other part, which is if your function is very complex and complicated, not simple. But for the simple function, your perceptron, your system, even though it's initialized with random numbers, it will learn. So the weighted sum now, the weighted sum of the inputs is then applied to this hard limiter or this activation or transfer function. So in this case, we use the hard limiter. So this will produce an output equal to +1 if its input is more than equals to the threshold, and either if you're using the sign function, you will get a negative value. But if you're using the hard limiter, it will give you a 0 otherwise. So this is as simple as that. So you can clearly see that it's so simple, and also it's one of its advantages. The simplicity of the neural network, the core processor, which is a perceptron, the neuron, is also one of its major attractiveness. So it's very simple. You just add the weighted inputs and then you compare against activation or transfer function, and voila, you get the output, either a +1 or a 0. So far, so good. So this is the visualization of your simple perceptron with 2 inputs, and this is the one you will use for your lab, the last lab practical. Last lab practical, number 4. I think we will end it next Monday morning. That will be probably I think there's a last lab, if I'm not mistaken. I think so far we have done 1, 2, 3, maybe one more. On Tuesday afternoon, there's one more. One more group. So if you can see the visualization, I've done some little bit of animation. So basically, the perceptron here consists of two basic functions. It will do two calculations if you like. Right. First part is actually it will sum up. It will do a linear combination. Linear means it's actually multiplied by the weights. So in this case, there's one weight for each of the inputs, and then we'll combine them. You sum up everything. The output of that, the actual answer here, the value here, which is summation, will then be compared against, or will then be compared against what do you call it? The transfer activation function. So in this case, I can see here we are using the hard limiter. So there's also a threshold. The threshold will move so it will also define your hard limiter or transfer function, and then you get the output. That's it. This is what the perceptron is doing. So there's no magic to it, and it's simple as that. But when you combine large enough numbers of this perceptron and put enough layers, it can do interesting things. I'll call interesting things which will amaze many of us. So the aim of the perceptron is to classify. Now there's a new term here to classify, to actually identify input example into say one or two classes. Say A1 output, if the output of the neural network is equal to 1, and A2 if the output of the neural network is either equal to -1 or 0. So for a simple output here, I can only have two classes, correct? Because the output can only be a +1 or -1 or a 0 or a 0, depending on whether you use a hard limiter or you are using the sine function. But of course, if you say, oh, I want to use more classes, I want the system to actually identify, to classify, to grade, to identify more classes, then of course you have to change the output now. Instead of one neuron, you have maybe a few neurons to satisfy your requirement for multiple classes. Now, in the case of a single perceptron, the n-dimensional space, because of your input here, right, the n-dimensional space, because if depending on inputs. So if you have two inputs, it will be two-dimensional space. If you have n inputs, it will be n-dimensional space. Follow? So this one will be, then the n-dimensional space is then divided by the hyperplane into two decision regions, because this is a single perceptron. As I mentioned before in the previous paragraph or previous sentence here, because it's a single perceptron, I can only have either a +1 or -1 or +1 or 0, depending on my transfer function. So, but the inputs, I can have many inputs. I can have many inputs, and then as a result, I can then grade them into yes or no, black or white, right? Apple or oranges, things like that. And this is actually divided. This is actually separated. The two classes, A1, A2, are divided by this hyperplane. Now, why do we call it a hyperplane? Because it is n dimension, right? If it's 2 dimension, it's a line. 3 dimension is what you call it, three-dimensional space, a plane. But if you have more than 3 dimensions, how do you call it? What do you call it? That's why you call it hyperplane. So there is perhaps a new term for some of you. Now, this hyperplane can be defined by the linear function. So this separation plane can be defined by this linear function. Now, we notice this. The first part here is actually your here. It's a summation of the weighted inputs, and then you combine or compare against the threshold theta, which is here. So from that, you can see, and then this will give you 0. So that's how actually this is actually, so the trick is actually to find the correct hyperplane to force the perceptron to able to separate the two classes nicely. So that's a trick. That's the trick here, and it's to train the perceptron. Now, what do you mean by training? Right? Training, actually, you look at it closely, it means that you're actually modifying the weights over here. This inputs, you cannot do anything, it's fixed. But this fella, you can change. Because it's initially, as I said, you initialize it with some random values, more values. As you'll see later on, you don't, of course, put too large values. And I think there has been considerable studies in the past, maybe 50 years, Actually, I think that area is actually people don't touch it anymore because it's actually quite stable, quite mature. You know that the weights had to be initialized, but to some small values. If you initialize the weights too large, it will tend to not able to learn, right? Then it will quickly run into a different direction and give you wrong results. So this is one area that's been studied quite a bit, and people just accept it now. The weights must be small. It cannot be too large. Of course, the question then is how small is small, but then there's a rule of thumb. There's a rule of thumb telling you how small it should be. Yes, so far so good. So now this is a visualization of your classification hyperplane. So what does it look like? As I said before, if it's a two-dimension, x1 and x2, if it's two inputs, then the hyperplane will be basically a line, right? A line separating the class A1 and the class A2. So you notice again, for some of us who may not be familiar with the term classification, actually I've been using the word class A, class B. So the act of classing it or separating the two classes is called classification. For the word class A1, class A2. So once you've done that, you can see here, right? This equation here would define um, your plane, which is a line, a nice line separating the A1 and A class A1 and A2. And I think we will study this in more details. This particular interesting fact, this plane or this line that separates the two classes in the advanced topics called support vector machines. So you can also some people have actually argued that the support vector machines is a specialized class of it's a special class of artificial neural networks. It's not that alien. It is actually extension of your artificial neural networks. Now in the right hand side here, now instead of having two inputs, now I have a three input perceptron. Because the classes, the inputs now have three dimension. I'll need to again, because each of the points, each of the representation of the class A1 and A2, still A1 and A2 because the output is only one neuron. One neuron, so I can only have two outputs, two possible classes A1 and A2 because of the single perceptron of single neuron. So what is the separation looks like? It is now a plane. I can see here a plane that will separate the two classes in the two classes inside that three-dimensional space now because of the three inputs. So you can see here the equations now are getting a bit more complicated. Of course, it is not possible for us to actually draw n-dimensional space, right? Of course, if you can do it, please let us know. We'll be happy to see how we can use that information and the trick to draw three-dimensional space, n-dimensional space. So that's why we stop at the three-dimensional space for us to visualize. For n-dimensional space is not easy to show. And of course, in the real world problems, difficult problems, real world problems, of course, it will not be just three dimensions. It can be many dimensions. I'm now looking at a problem, which is actually to recognize the ripeness of the oil palm fruit. And so far, I'm looking at about 14 dimensions. So you can see here, if it's a 14 dimension, in order to solve the equation here to separate only just two classes, it's not that straightforward. It can be quite tricky. It can be quite challenging to do that. Of course, as I mentioned before at the start of this paper, the introduction, that's why we're here. Engineers are supposed to solve tough problems. If it's simple problems, ask yourself, if you are the boss of a company, why would I pay good money to hire engineers? Engineers now, I think starting pay is about 3,000. I think Intel's about last time I checked was about 3,200. I think Intel was paying 3,200 for the what they call the contract engineer. They call it. I think it's something like that, right? They I think maybe I'll talk to you separate privately, because we saw something interesting with Intel strategy because they hire a lot of engineers, but so that but if of course if you cannot last, if you cannot take up the challenges, cannot perform well, they also because it's contract, so they will say thank you, bye bye, see you again some other time, and that's it. So they only retain a small number. So that's why they're using employing this strategy to attract the brightest, the smartest engineers. But at the same time, they take a lot. Then for them to select the better ones, he will stay. The rest will say bye bye. Thank you for helping us. Now, this is an interesting slide to show you to explain to you the linear separability of perceptron. How does the perceptron separates, right? The two classes. Again, we're talking about single neuron. So here down here, we are looking at the two-dimensional plots of some of the basic logical operations. Some of the basic logical operations. What are they? The leftmost A, it is your n function. Now you can see an n function, and also we have I've shown you here highlighted in black one class, and then the one in white, the circles in white are the other class. So if you can see here that only when the inputs, two inputs x1 and x2 are 1, you get the 1, which is represented as a black circle. So here I can say that the black circles represent the logic 1 state. Logic 0 states are represented by white circles, correct? White circles, you can see here. So this is your n function. Now the one in the middle, or B, is your all function. So all function is, except for both the inputs are 0, otherwise all the outputs will be a 1, as shown here. So in this case, this is a reverse of this. This one is everything is 0 except when both inputs are 1. That's why you get the black dot over here. This one you get 3 black dots. So as a result, if you were to look at it visually, what can you see? What can you see? I can easily draw a line to separate my two classes between the black circles and the white circles here, this line. So the one in blue here, this area blue, will represent the logic 0, and anything above the line here will represent logic 1. Yes? So far, so good. Now, for the all function, you can do the same thing. Now, notice that here, now my line here, my dividing line, which is my hyperplane, but in this case, since it's 2 dimension, it's just a line, will be shifted down here now, closer to the 0 over here. So anything above the line here will be logic 1, and anything below here will be logic 0. The last one over here is your exclusive OR, which is now exclusive OR. If you are still can remember, if the either of the if the inputs are not the same, means that x1 is a 1, x2 is a 0. X2 here is 0 over here. So x2 is 0, this point here. X1 is 1, x2 is 0. Output is a 1. Now, then if your x1 now is 0 and your x2 is a 1, you still get a 1. Otherwise, you get zeros here. So looking at this, can you tell me how to draw a line to separate the black and the white? One line. Right? Can see here, it is not possible. So what does it mean? You look at the bottom here. So the perceptron can learn the operations n function by drawing a line, the separation line between the two classes for the n and the all functions, but not the exclusive OR, because here I cannot draw a line. So that is the limitation of my perceptron. It cannot learn. It cannot learn the hyperplane for my exclusive OR. So important message here is what? Important message here is that the perceptron can only separate linearly separable classes of A1 and A2. This is not a linearly separable class A1, A2 for exclusive OR. You cannot, the perceptron fail So actually, that was one of the reasons why, in the early days, there was Minsky and Papert actually was suggesting that perceptron cannot, the neural networks at the time is useless. Cannot do interesting things. When it gets too difficult. So how does the perceptron learn its classification task? So you can see here, if I were to show, I want to train the network to learn the end function or the OR function. How does it work? How does it work to actually give you that train network to actually tell you to be able to then can use it to perform the end function or the OR function. Now, this is done by making small adjustments in the weights to reduce the difference between the actual and desired outputs of the perceptron. A few major points here to highlight is by the network, actually the training method, the training algorithm, does it by making small adjustments, not large, small. That's why it's little steps. In the weights, you change the weights. So actually, the learning is actually in the weights, which is the same as a human brain. Our synapses, the interconnection, the weights in the interconnection between our brain is the one we actually, scientists actually in particular, neuroscientists have shown that that's how we humans learn, or animals learn for that matter. I don't think we did much work on the human brain, but more probably on the monkeys. Now you adjust the weights here to reduce the error, or difference between the actual and desired outputs of the perceptron. What does it mean? It means that your problem you're trying to solve, the function you're trying to learn, you already know you already know the desired outputs. So for the end function, I know that 1 and a 1 give me a 1. So I know that for the input of 1 and 1, I should see a 1. So but then in the training phase, maybe the actual output is not a 1 yet. So that what is the difference? So you have to, at that iteration, you have to make small adjustments to the weights to make sure that finally your actual and the desired are the same. Finally, your actual and the desired outputs of the perceptron are the same. As I said before, when you start with a brand new perceptron network, the weights have to be set. The initial weights are randomly assigned and then updated to obtain the outputs consistent with the training examples, which is back here. Input is a 0, x1 0, x2 is a 0, output is a 0. There's one state. Another state is with the input x1 equals to 1, x2 equals to 0, output is also a 0. There's a second state, and it goes on. That is you show it to the network. The network will say, and then network will calculate. The perceptron will calculate and see what is that, give you the actual output. Then you compare against the desired output to calculate your error. Is the error, then you have to basically minimize the error, reduce the difference between the actual and the desired outputs of the perceptron. Right? Can follow that? Of course, I think, okay, never mind. So you then, the initial weights are randomly assigned and then updated to obtain the output consistent with the training example. So the more training you have, the better I will learn. Now we're going to the bit of the mathematics behind it. Now, if at the iteration P, so P is now used to represent iteration, the output is Y, actual output is YP. This is the output of the perceptron is represented by YP. So output is Y, and at that time, iteration is P. And the desired, what you actually wanted, what you hope to see is actually subscript D at that time. Then the error is basically very simple, right? You just take the difference between the desired and the actual. Actual means it's the actual output from the perceptron network. So P is your iteration. So you have to keep running it until your error here is at a state whereby you are happy. So you can now see already, there's a bit of a trick involved to actually identify what's your EP. If your error, if you want the error is to stop, is too small, is small, you take a longer time, right? Compared to if the error is not so small, right? The thing will converge. This error will achieve this at the early stage. But the downside is, the disadvantage is that the downside is you have a larger error, so the network may not be able to function the way you want it with a high level of accuracy. Now, your iteration P here refers to the P training. This is under training. So once you train it, you don't have to worry about training anymore. So there's no P involved. Just straight away put it inside and then it will give you the answer. Now, to reduce the error, the weight values are modified according to the perceptron learning rule. So we are also told that scientists have studied this for a long time and they find that this perceptron learning rule works very well. So actually, it's been accepted that this is the best perceptron learning rule you can have. And then they use it to reduce the error. Of course, nothing is perfect. Of course, there will be variations. There will be variations of the perceptron learning rule, maybe to make it better. Most of the time, the perceptron learning rule is good enough. Now we come to look at the perceptron learning rule. So you can see here the perceptron learning rule basically looks at the weights. So your P are your what you call your iterations. So the new weight at the next iteration, P plus 1 equals to the old weight, right? Plus the product of alpha multiplied x of I, which is your input, multiplied by the error, as shown in the earlier case, in the earlier slide, which is your EP here. So this is the actual perceptron learning rule. And I think this rule is actually given in your last page of your exam question paper, right? But again, in the current norm of having exam, right, when it's open book, so you can also refer to it in from your own notes. But of course, if you refer to it, you might have to take some time to actually find the right page and the right equation to look at. So that might waste time there, right? But of course, if this is provided in the exam paper, better still, right? So you at least don't have to look for it with much effort. But of course, better still, it will be if you don't need to refer to it, you actually can remember this perceptron learning rule. So here we know what is W. This is the weight of the input I, and P plus 1 is the new input, a new weight at the next iteration, and this is the old one. But the thing new here is the alpha. What's alpha? Now, alpha is the learning rate. It is normally a positive constant, less than unity. So alpha is actually lies between 0 and 1. 0 is very slow learning rate, and 1 is the best, right? So as I said before, this is something you can tune the network. If it doesn't learn the first time, you can tune it to make sure maybe the step is too fast, the thing is not able to learn. So same thing, I think if you look at it closely, it's same as like human, like all of us. If I were to speak very fast, I think, and then 1 minute finish everything, I think we have great difficulty learning. So this in the way it symbolizes the closeness or similarity between the artificial neural networks and the human brain or the human biological neural network. There's a learning rate. If its learning rate is too high, we find that we cannot learn. So normally the learning rate is quite small. So EP is the total error of all the all the inputs, not just one, not just I, right? You can see here the major difference is that this is all of subscript I except for this one. This is the total error of the whole network for that layer. Now, this perceptron learning rule was first proposed by Rosenblatt more than 60 years ago, right? More than 60 years ago in 1960. So using this rule, we can derive the perceptron training algorithm for most classification tasks. So it can be used to actually differentiate between class A1 and class A2, or class A1, A2, A3 for that. Now we're now looking closely at the perceptron training algorithm. It consists of a few steps. So the first step is, as you may have guessed, it is to initialize the weights. So that is your initialization step. So in this initialization step, you set the initial weights, uh, um, which is tied back to your number of inputs. If you have n inputs, you need to set n of them. So random numbers in the range now. So the initial weights can also take on negative values. So that means that what does it mean in reality? What does it mean when you have a negative weight? That means that that contribution to the network itself, to the perceptron, is too high. I want it to be lowered. So it shouldn't. I do not want to listen to that input too much. That's why I'm now saying I want to reduce your influence. I want to reduce. That's why I'm putting in a negative weight to reduce your influence. For example, let's say I'm now seeking advice from all of you, 90 of you, right? So if I were to think of yourself as the inputs to me, I'm the neuron now, I'm the processor, the perceptron. For some students, I say no, I would reduce your comments by having a negative weight. And then for some, I think I trust you more, so I'll give you a higher value or positive. Now, these initial weights you can see, commonly quite small. It should be within this range. It cannot exceed zero point 0.5. It's 0.5, you find that your network will actually will have great difficulty learning. So that's why studies have shown that this is the best range. So this one, as I said before, this is more or less stable. So there's no need to actually try to figure out what is the best set of weights. But in the early years, when people were doing research into neural networks, I think there was some work done to find the best set of values for the weights. At number two, now you activate, right? In the perceptron training algorithm, you now activate the perceptron by applying the PEAT example, which is your iteration, right? So at that point, at that iteration, what patterns you want? You want to show to the perceptron. So in this case, for the uh, n inputs system, x1 to xn, and then you calculate the actual output. So it's where you now calculate the outputs after initializing the weights, as shown here. So these weights will be initialized, and then you calculate and you total up inside this square bracket. So if you have n inputs here, you sum up or you multiply the inputs by the weights, and then you minus the threshold theta. I will come to the theta later on in the maybe next few slides. So here n is the number of inputs to the perceptron, and the step here actually is your transfer function. In this case, we are using the hard limiter or hard limit activation function. Now you can also see that we are also not limiting your activation function to just the hard limiter, but we can also saying that you can also use your sine function. Now, in the next lecture, you will find that there's also other types of transfer function you can use, which is your sigmoid. That one's another story. On the next day, we'll come to that. But for the time being, for this perceptron, especially want to use it on the example of your logic function, the Boolean logic function or n and all, you will use the hard limiter activation function. Because the hard limiter means that it will constrain the outputs to be 0 and 1. Right? So in this case, logic 1 is 1, logic 0 is a 0. So we don't have the logic 0 equals to minus 1. But of course, maybe for your application, you want to use something negative, you can also use a sine function to accomplish that. Number 3 now. First step. Once you calculate the output, now I will not want to train. I want to adjust my weights now. So you update the weights of the perceptron, right? Depending on I think you'll see here, as shown below. The new weights here will be the old weights, and then plus a small slice, right? A small slice of your difference in the weights. So with this delta WIP, is the weight correction at iteration P. Now, this weight correction is computed by what is known as the delta rule, as shown below here. So your weight correction term equals to alpha times your input at the O input multiplied by the total error. Right? I think this one is shown before in one of the earlier slides. And the next step, after you calculate you have modified the weights, modify the weights. This is actually how much you want to change the weights is defined, is actually it's controlled by your training rate, which is alpha. So now after that, after calculating the changing the weights, now you move on to then you try again. Repeat the process, increase the iteration by 1. So P by 1, and go back to step 2 and repeat the process with the next training example until convergence. Until it converges to something. The total error is a good way to measure to stop, to tell you when to stop the training. Otherwise, it can go on for days and days. Especially if you have a slow processor on your PC, on your notebook, right? So that's why for this kind of work, you need a fast processor. Otherwise, it takes few days just to run one set of inputs. Now, for the training of a perceptron, basically convergence means the actual output for all training examples matches the desired and target output. That is, all training examples are classified as desired, meaning that if I input 0, 0, output should be 0 for n function. The next time, not only one input, you need to try. You need to be able to convince yourself that all the inputs have been, the outputs are satisfied for all the different inputs. So for 2 input AND gate, it will be 0, 0, 0, 1, 1, 0, and 1, 1. So every time for those 4 input combinations, my output should be 0, first one, 0, second one, 0, third one, and lastly, for 1, 1 input, it should be 1. All of them should be as desired. This is your desired. And it must satisfy that. Otherwise, you repeat the training. Okay? Now, number 5 now. That is only for one iteration within that 4 inputs. After that is finished, you then repeat. So when you have 4 examples, right, in the training set for the AND gate, 2 input AND gate. Now, when all examples in the training set have been used in the training, then you start a new epoch. You need new iterations or epoch by continuing with the first example until convergence. So you can see here, iteration within iteration. So this is one epoch when you have to present all the possible input combinations. Right? So now if I were to give example in your assignment, right? So if you divide your data set into 70%, 70% of your 63 input patterns, which will be about 21 times, 0.7 now, about 14 times 15, 15 times 3, 45 different input patterns. So you need to present all of them one by one, 45. Once you finish that, you get the error. Then you now go back, start a different epoch, and you present again another time for the 45 training examples. And you keep repeating until convergence. What does it show you? There's a whole lot of calculations going on. Right? I'm reminded by the song, the old song. I think most of you will not know this, but there's a song that talks about whole lot of shaking going on, because shaking here in the use it in the sense of dancing, right? Whole lot of shaking going on. So in this case, whole lot of calculation going on. A lot of calculations. That's why that's like I think that's why I think you look at it closely. That's why we have to wait until these few years for these neural networks to take off, to find acceptance, because in the old days, your computer is not so fast, right? The processor is not so fast. To do one calculation takes you long time. But now with the what do you call it, chip, with the availability of chip, right? Chip processing power, right? Again, this is again back to cost, because if your processors are expensive, right? Not many people, not many companies, not many students will be able to utilize, able to enjoy, use those artificial neural networks to do something interesting. And so, of course, once you do it, the companies, not many companies will buy it because it's too expensive. But because of the availability of both cheap and powerful computers or processors, right? Your NVIDIA, those kind of things, GPUs, and it's cheap and it's also fast, powerful, combined together, right? That's why you have these artificial neural networks in many people's lips. People know, I heard about artificial neural networks. I heard about deep learning. It's only now. Plus, what's the other part? The other part is also all these powerful training algorithms coming up from the research labs, from the coming up from the all the universities who are doing work in the area to improve their artificial neural networks. So we believe that there are three uh, main reasons: cheap computing power, powerful computers, and also powerful training algorithms. Okay, now I think we almost come to the end of this just nice of this particular topic on the introduction to artificial neural networks. Now we have, assuming we have a two-input perceptron, two-input perceptron. So you can see here, I equals to 1 to I equals to 2, which have the following input to output mapping. Right, this is your step function. So now, where x is the perceptron input and weight is the weight, and then step function denotes the step function, threshold is set to 0.2. So now I want you to look at the weights. This perceptron is used to learn the binary logic function OR. So which is 0, 0 give you 0, 0, 1 give you a 1, 1, 0 give you a 1, 1, 1 of course also give you a 1. That is your OR logic function. Now, you also furthermore, you are told that the initial weights of these two inputs are 0.1 and minus 0.3. So you are told that, right? So now you have to construct a training set of 4 examples. So as I said, the training set will consist of what? 0, 0, output is 0, input 0, 1, the next one will be 1, 1, 0, input, give output of 1, and a 1, 1, give you a 1. So this is your training set consisting of 4 training examples to train this perceptron to learn this OR logic function. So you have to demonstrate a training epoch of the perceptron, just one, which must involve all the training examples in the set. Now, furthermore, and lastly, you're told that the learning rate is 0.1. So everything is given. Right? Learning rate is 0.1. So basically, you have to apply the rules as we discussed just now. So here, this is the first step. You have to write down, at least on paper, to clear your mind that this is my logic function. So this is the first pattern: 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. So the perceptron learning epoch is actually, I need to present 4 of them. Right? 4 of these training examples considered as just one epoch. So here, 0, 0. My output target is, desired output or target is 0, 1, 1, 1. Initial weight is 0.1 minus 0.3. This is the first set, right? So of course, question is, do I have to start with 0, 0? No, there's nothing to say that you must start with 0, 0. You can also select any of these patterns randomly to actually train your network, train this perceptron. But of course, this one is something we just, for convenience, we select 0, 0. Right, so in this case, 0, 0, and we are told that initially the weights are 0.1 and minus 0.3. Now, once you do that with the given values to the various parameters. Theta is 0.2, I believe. Theta is 0.2. Right, and your learning rate is 0.1. Right, so based on that, you will then calculate the error based on the equation that we have discussed so far. So from there, then we also see how does the weight changes, how are the weights modified. In the first example over here, 0, 0, and the output of 0, you find that there's nothing changes. The weights are still remain the same. 0.1 minus 0.3, 0.1 and minus 0.3. So this is now you then use back the same weights in the second iteration. P equals to 2 now. When you present the second training set of 0 and 1. Now the weights now are actually taken from the new weights, right, which haven't changed from the previous iteration of 0, 0. They are taken from there. Over here, they are now put here because all this should be 0. Right, 0 because now I'm now using it now. I can use it now because from the starting point of 0, 0, I got 0, 0.1 minus 0.3. Now, since the weights do not change, I'll put them here now. And then you look at the output again. Actual output is also 0. The error now is 1. Right, but why is it a 1 here? Look at it. This is the all function. All function means that my actual output should be a 1, but I'm getting the output of 0. So there's a big error here because I'm not able to learn that output is a 1. I'm now telling you output is a 0. So that's wrong. So error is a 1. As a result, you can see now something is wrong. So as a result, you then modify the weights. Now you can see here the weights actually the second one has changed. So the second one, I think we should say that the contribution from the second weights should be higher, not minus 0.3, but now reduced to just minus 0.2. I want to listen to that input more because I find that it's not giving me the right answer. So these sort of weights here, 0.1, the new weights are 0.1 and minus 0.2 now is now put there for the next pattern of 1, 0 for it to network to calculate again. So you can see here, these new weights are now put here for you to calculate the new set of the actual outputs for the input of 1, 0, 1, 0. So in this case, even though they put the new weights here, I still get the actual output which is wrong. I still not learning well. I still say it's 0, right? So you can think of it as very stubborn. I say it's 0, but it should be a 1. But the network is still telling you it's a 0. So it's wrong again. So now go back and then you see how should I modify the weights further. How do I modify the weights further? I can see here. And now I can see here I will have increased my weights for W1 to be 0.2. My weights for W1 to be 0.2, but my weight for for input 2 remains at minus 0.2. And these two new weights are now used in the final iteration of the final pattern of 1, 1. What I can see here, 0.2 minus 0.2 is put here and is used in the final, in the calculation of the final set of inputs of 1, 1. Now, based on the final inputs of 1, 1, I will now again calculate what is my output. The actual output based on these weights and based on this input, and then you can see here, output is still 0. It is still wrong, although it should be a 1. Still wrong. So the error is still high or 1, and then I can see here now, I have now increased my weight W1 to be 0.3, and also I've increased my weight for W2 to be, actually both have increased to be minus 0.1 from minus 0.2. So this is just one epoch, one round for the 4 inputs, and it's still not learning. Right, so again, of course, you can carry on to do the calculations for the next round, for the next epoch. You present again the 4 input patterns, and then you see what is is able to learn. Right, so you can see what you see here. You can see that unless you have a fast computing power, there's a lot of calculation going on, and it's slow. Right, so it's not
not advisable, not recommended to do it using pen and paper. Right? You can see a lot of calculation, and then of course, if you're using pen and paper, even a calculator, you find that you can easily make mistakes. The calculation itself is not that difficult. It's actually quite straightforward. Sum out everything, multiply by the weighted input, sum out everything, compare to the threshold, and then give it a small learning rate and see what's the change in your weights, and keep repeating until error becomes zero. That's it, right? Simple as that. So as I said, this question only asks you to do one epoch. So again, in the exam, such questions can come up, right? Maybe you ask you one or two just to show your understanding of the problem. So, but you ask you to prove or show that it actually converges, right? And somewhere along the way, if for some of you, if you make a tiny mistake in the calculations, you find that after uh, calculating 10 times, 10 epochs, you're still not able to converge. So that's very stressful. So we wanted only to ask you to show maybe one or two epochs to show that it's actually converged. So please be careful in your calculations to show that actually it's able to 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 uh, to prove that what's the actual outputs or outputs the output state of the network. Now in such a case, you also advise. Uh, I think in all the papers that you sit, right? So we actually looking at your understanding rather than the answer. Of course, we also look at the answer, right? The answer is, of course, the answer is correct. So we assume that we can safely assume that your calculations are correct. You use the right equation and you're able to move the values into the right place for the next calculation. Now, what happens if your answers are wrong, totally wrong? But somewhere along the way, you showed that you're able to answer it. You understand the concepts. So that's why you are highly advised, right? For those of you who are paying attention, highly recommended to actually show your working every single step in large enough letters. Don't try to squeeze everything to be very small. That I have difficulty reading, right? If I make a mistake in reading your answers, right, then it's your loss. So try to help me also, right, to write large enough in a very black using black ink, clear black ink to show the answer. So if your answer is wrong, but your steps are correct, you still get about 80% of the marks because I know that you somewhere along the way you make a mistake. But if I will mark very strictly, you get a zero. I think it's also not right because you make a mistake there, right? And it's not because you don't understand. You understand, but somewhere along the way, instead of writing a 3, you write a 8 there. So that's changed a lot, right? Instead of using 3, you use 8, number 8 as a value. So they changed a lot. But your steps are correct. So at least you still get some most of the marks, right? So that's why I say make sure you write down all your steps, and also especially in this what do you call it, in this new norm where it's open book test. So also they also to prove that actually you did yourself and you did not get any help from anybody to get the answer. So because if you show only just the answer, if the answer is wrong, of course you get nothing. But if you show the steps involved, at least you still get something out of that. Okay, so that's nice. We stop. We can finish this part here, this topic here of the basically introduction to your artificial neural networks. So we also look at was the motivation. What actually motivated us to actually study to propose artificial neural networks? Because I think if you remember, we are motivated by the fact that the human beings are able to do some things much better than machines. So can we copy that uh, into a artificial system? That's why we have this artificial neural networks in concept. It's based on the human brain, or our brains are biological brains. Then we look at some of the common architectures. The artificial neural networks is not homogeneous in the sense that there's only one network. There's many different networks, and there's also other major important characteristics of such artificial neural networks. We then look at how the field itself has evolved. The field of artificial neural networks has evolved, and some of the key developments and some of the key people who has helped to develop the field. I am reminded of this very wise saying that in order to know how to move forward, you need to know where we have been, where we were before. That's why history will point the way to the future. Right? We need to know, is it something solid? This artificial network, is it come from thin air? Or is it something based on some solid foundation? So that's why we look at the how the field has evolved. Artificial network. So can see here actually has a long history of more than 60 years uh, in the field, and then that's where we are today. Only recently as in the past maybe 5-6 years, you see a great explosion of interest in artificial neural networks. And I think you look at it, so far I don't think any of you are actually looking at uh, some of the simpler neural networks. You're actually looking at the tougher ones, and I think we will go into that and understand why we actually are able to do it now. In the last hour or so, we studied the perceptron, the simplest of all the artificial neural networks, which is basically just a single neuron, and see how it actually we can use it to perform some interesting function. For example, trying to learn the simple biological function, not logic, simple binary logic function, right? Binary logic function, not biological, of all function, or even the n function. We find that it cannot learn the exclusive OR because it's not able to, because it's not linearly separable. That's why with great difficulty doing that. So okay, as a result, the perceptron will not be able to learn the exclusive OR function, but can learn the simpler uh, n function and the OR function because the two classes here are linearly separable. So with that, we conclude the topic on introduction to artificial neural networks. Just a quick announcement, because next Tuesday, 31st of August, is a public holiday, right? It's an odd week, and then there are two tutorials will be affected because we will not have a class on that day, so as a result, we will now replace because of the policy of the university, we have to replace all classes. So we will replace the class on Wednesday, 25th of August, which is next Wednesday morning. And that's only time that I'm quite sure you are free. And then this was the time given to me by the faculty office. So please, those students who are affected on the 31st of August, your tutorial, please be informed, right? I'm doing it here again, just to make sure you remember. And also, I've actually posted this on the Google Classroom. But just a quick reminder again that your class will now be replaced on the Wednesday morning starting from 8 a.m. And this is the RE4 Group 3, consisting of students like Ang Kai Liang, Chang Jun Weng, etc. That group of students. Please come in 8 o'clock on next Wednesday for your tutorial. Now, after that will be the RMS 4. Continue the same thing again. Chan Boon Hong, this class is group 1. Chan Boon Hong, Chi Wing Kang, Christopher, and Chong Jian Kai, etc. Now, where do you go? You join back to the tutorial Google Classroom, right? Google Meet for that. So this is just a quick reminder. I posted on the Google Classroom, and I'm now making an announcement here again. I made an announcement yesterday as well. No, Wednesday, Wednesday again. So this is you can't say you're not aware of it. So again, just a quick reminder again for those 3 students are yet to receive your reports. Maybe you've submitted and it went somewhere else. So please resubmit even if you have if you've done it. Make sure that it's submitted on using the Google Classroom. So with that, I'll stop here and then I may break before I start the next topic on the multi-layer perceptron. So any questions? Okay, so I stop the recording. I will continue with the next topic. So we take a short 5-minute break. Come back. Okay, I just saw a question from Jun Hao. Jun Hao, can you explain? You're referring to the last part. Is it the question on the perceptron? Am I correct? The all function to calculate. Is it? Am I correct? Let me see. What your? Sorry, I didn't see that. I think I didn't see that. Okay. I know this is not the question. I'm just saying that in case there's a question here. First question here will be probably be the second part of the questions. If you look at the past year questions, the questions have two parts. First part is actually testing your theory, understanding. For example, what is fuzzy logic? What is artificial intelligence? Can intelligence be measured? What is the best way to measure intelligence, for example? So if then the next part will be calculations to see whether you know how to apply some of these basic concepts, right, related to each of the topics here. So in this case, it depends. Probably maybe 60%, maybe 10% or 10 marks or 15 marks, all of the 25 marks. So I think it's not, I think, how should I put it? It's not correct to actually give everything to just one question where you just calculate. So it will be breaking the two parts. So for that, for your question, I think you have to go back to refer to the past year questions. So, but what I know is that it won't be the full 25 marks. 25 marks will be more of a class assignment where you have to calculate. So in this case, not only are you good at understanding the equation, how to use the system, but you also have to explain, show your understanding of the theoretical aspects, as I just gave just now in the two examples before, right? So rest of you, please take a break, and then we come back on a new topic, which is what I'll set up. Yes, sure. You can see I will. Give me some time. I will do some editing to clean up some of these things. I think are not relevant. So clean them up, and I'll upload because this one actually is a combined. I think over 3 lectures, I'm not mistaken. So I need to combine them. So I will definitely upload. Right. So please take a break. I will start about say now it's 11:09. So maybe you start about 11:15. Right. Thank you. Good morning again. Welcome to this new topic of multi-layered neural networks and the back propagation learning algorithm. So, what are the learning outcomes? What do you expect to learn from this particular output? Uh, for this particular topic. So, we will learn about the multi-layered neural networks. Then we will spend some time to actually understand and use how to use the back propagation learning algorithm. So there's another. I find that maybe the book itself by this the one on the intelligent systems uh, by Professor Nowinski is maybe not sufficient. You can also look at quite a good book on the in the library, which is basically an introduction to neural networks by Kevin Gurney. Although it's a bit old, but it's a good introduction to get you started. Now let us revisit the perceptron. So you can see here, this is a more detailed representation of the perceptron, consisting of few parts here. You can see here the inputs, and then they're all connected to the weights, right? So, and then this all sum up, computation, and then once you sum up everything, then you just apply to a activation function or the non-linearity. And then is where you get the output, depending on your activation function. So in this case, I can clearly see that we're using the sine function. If the total of the output is more than 0, you get a 1, right? Otherwise, you get a -1. Now, I want to also draw your attention to this representation of your perceptron. Notice here, there's a 1 instead of x1, there's a 1 here. So this is a different representation of your threshold, or your, remember in the earlier example of theta, which is your threshold. So the bias of the threshold can also be represented as simply another weight. This weight is actually W0, right? With a constant tied to the constant input of 1. So in this case, probably you get a fixed weight, which is your theta, right? You can see here theta. So your W1 times your, W0 multiplied by your 1 actually is your theta in the earlier representation. So in this case, you can see that my W naught will be basically negative, which is represented by my theta. So this is another way of representing it. So you don't see that threshold anymore. It's actually embedded inside the weights here as another input. So just a quick revisit of the perceptron. The bias B1. So I think we've seen before in this case here, right? So you can see this bias here. Now, some books say that some references suggest that they are different. So your B1 is not the same as your inputs. Now, however, practitioners means that people who who actually uses the perceptron have suggested to set the threshold to theta and only use it as a bias based on the threshold. So both bias and the threshold do the same thing. It is a shift the activation function along the x-axis. So this is another way of looking at it when you have your threshold and your bias. So there's one bias here. So your theta is your, what do you call it? Your theta is your some papers or some books say that the bias and threshold are different. Right? That's what we are saying, right? They are different. But so far we have not looked at the bias. We only look at the threshold, which is your theta. Now, whether you're using the bias or using the threshold, you find that they actually do the same thing, which is to shift the activation function, which is your hard limiter or your sine function along the x-axis. So with that, let us now go into the multi-layer neural networks. So a multi-layer perceptron is a feed-forward neural network with one or more hidden layers now. So that is the, can see clearly see that there's a major difference now. We are now looking at the feed-forward neural network with one or more hidden layers. Now the recurrent or the one with feedback, we will not look at it now, but we look at it in the near future. In the next few lectures, we'll touch on a little bit on that in the next lecture on the feed-forward neural network. So now the main difference is that, as the name suggests, is multi-layered. So just now we look at the perceptron, it's only one layer, one neuron. Of course, you can also have many neurons in that one layer. But here we're looking at multiple layers consisting of multiple neurons for your this multi-layer perceptron. Basically, you look at it. Basically, it is some most of the time people people don't call it multi-layer perceptron. It's quite a mouthful. So it's just called MLP, which means multi-layer perceptron network. Now, what does this multi-layer perceptron network look like? Basically, the network consists of an input layer of source neurons and at least one middle or hidden layer. We'll come to that. We will see why it is called a hidden layer later on. And at least one middle or hidden layer of computational neurons. So basically, it says that it consists of at least one middle or hidden layer of these neurons, and an output layer of the same processors, which is your computational neuron based on the perceptron. The input signals are propagated in a forward direction on a layer by layer basis. This one we look at it in the next few slides. What does it mean? How do we calculate the input signals as it passes through the various layers in a forward direction? So basically, it's here. Look at it. Basically, we look at it forward means so say from left to right. If you're drawing inputs over here, so left to right. Okay. So you can see here, this is one example of multi-layer perceptron with two hidden layers as seen here. This is your first hidden layer and this is your second hidden layer. And of course, these are your input signals. Now, each of these, there are weights here. Although it's not shown here, there are weights. There are weights to actually influence or to change your inputs. Right? And of course, the learning algorithm will all the time will change the weights, modify the weights so that your output will fit what you want it to learn. So in this case, you can see we have the input layer, and then we have the first hidden layer. This is a simple example of only 3 neurons in each of the middle layers, middle or hidden layers. We will come to that later on, why we call it hidden layer. And then the last layer will be output layer, consisting of, and then you can actually see then you can actually measure the outputs of this. So again, this is just one hidden layer, and then you have 3 inputs and then 4 neurons in the hidden layer and 2 neurons in the output layer. So here, each of them. Now this one, the figure down here shows you the representation of just one neuron, just one neuron, and so you can imagine if one neuron, and then the inputs are coming from all the other inputs, right? All the other inputs. And then you combine them, you sum up everything, and then you apply a transfer function to it, and then you threshold this, and then you get the output value. Okay, so over here, okay, now these are the notice here, this is actually the input, and now we're looking at the input to my, so these are the inputs, and now they're moving to, we're looking at the combination of all the inputs, from the inputs to the neuron in the hidden layer. Then from there, we now look at the calculation, how the neuron in this hidden layer will then combine. So you can see here, just now early on, we look at it, the box here, the green box. So now this inputs, and then we're moving the three inputs here, and they actually combine they are actually merged and we calculated at the this neuron here. Now all of these are the same. So you can see here, all these inputs here are actually combined and calculated each of the neuron in the hidden layer. The only difference is that the weights are different depending on the function you're trying to learn here. So some will modify the weights, so some of these weights will be different. So although the inputs are the same, the weights are different, therefore the influence of each of these inputs to the neurons are different as a result. Now from here, we now move on to the, after you do your calculations for the neurons here, you will then combine them and then send out to the neurons in the next layer, which is your output layer. So that's how you combine them and then you get it in the output layer. So same thing, you do it for all the neurons and then you do it also calculate again for all the neurons in the output layer. Combine them. In this case, you have four. You have four inputs. As a result, the outputs of this become the inputs to the next layer. And you calculate again. And finally, you get it. Now, as I said before, we have another name for this middle layer is a hidden layer. So what does the middle layer, why do you use such a term? Why do you call it hidden layer? What does the middle layer hide? So the hidden layer over here, or middle layer, hides its desired output. So basically, what is the desired output? You have to you can easily calculate the actual output for the neuron, but what is the desired output? So it's hidden. You do not know what is the desired output at the hidden layer. So the hidden layer hides its desired output. And neurons in the hidden layer cannot be observed through the input-output behavior of the network. There is no obvious way to know what the desired output of the hidden layer should be. Here I know what is the out. I can calculate the actual and I can compare against my what I wanted, which is your desired output over here. I know what is the desired output over here. But how about here? I can also calculate the actual output, but how do I compare against the desired output so that I can then calculate the error? What's the error at the neurons at the hidden layer? Because it's hidden, that's why I cannot see it. So that's why the hidden layer hides its desired output. That's why they call it hidden layer. Now, commercial or practical artificial neural networks, especially nowadays when you use deep learning or deep neural networks, they incorporate 3 and sometimes four layers, including 1 or 2 hidden layers. Of course, each layer can contain from anything from 10 to 1,000 neurons. The experimental neural networks, I think those we call experimental, but nowadays actually it's quite common to actually have many layers. And I think a couple of years ago, when this Professor Loy from the Hong Kong University came to give a talk at our campus here in KL, he talked about his network consisting of 600 hidden layers. So 600 hidden layers, and of course, you can assume that each layer will not be just one neuron. Each layer will be consist of many neurons. So you can imagine the amount of computing you need, calculations you need to do for the 600 neuron. So 600 layer network, 600 middle layer network that was doing some work on deep learning. And then he was telling us that he had to actually speed up the processing. So he actually has to buy a lot of GPUs to actually in order for the computation to be completed quickly. And he then of course with you can also imagine the number of GPUs he has to use. So that one also needs need a lot of power and also need to generate a lot of heat. Plus the fact that it also occupies a lot of physical space. So what he did was that he had to rent out a room somewhere else outside his university, Hong Kong University, outside for him house to house the GPUs and also to and then connect back to his PCs at the campus to do the computation. Of course, what it means also is if you want to do serious deep learning research, you need money, you need budget. And the good news is that actually with his team of smart students, right, he was able to challenge even the results are better than Google. So imagine, you know, your results are better than Google. So actually, it's quite a he's a leading expert in the field. You can check his name out. And now I think now he's based in based in Singapore. Now he moved back to Singapore. By the way, he's a Malaysian. That's why he actually he came back to visit his family. So as a result, I said, why don't you give us a talk? So he said, okay, I'll give a talk to the students. So that's why a couple of years ago, he was very, we were lucky and also we were very fortunate. It was also kind of him to actually spend some time to talk to us about his work in Hong Kong at that time. And for those of you who are interested to do your postgraduate, you can also check him out if you want to study in Singapore. I think he's now at NTU, doing some work there. Now, one of the popular or well-known learning method in your learning algorithm to train your network for the multi-layer perceptron NLP network is your back propagation learning method. It actually addresses this issue because you do not know what is the desired output of the hidden of the middle layer. Therefore, I cannot use that to calculate. I cannot use that to calculate my error. If you remember, we talked about this before in the single perceptron. In a single perceptron, there's no hidden layer, there's no middle layer. So you can straight away know what is the desired output at that neuron that we have. So we have the desired, and then we calculate the actual. Based on the inputs we present to the neuron, we know the actual output, and then from the actual, we can calculate and compare against the desired, and from there we can calculate what is the error for that neuron, and then train it back, and then use that to adjust the weights to train the network, that perceptron, to learn that pattern, to learn that sequence of inputs. But for this multi-layered perceptron network, MLP, we cannot see the hidden layer or middle layer. So how can we then calculate what is the error? So therefore, we have to use a back propagation learning algorithm, as you now discuss in this slide and the next few slides. The good news is that learning in a multi-layer network proceeds the same way as for a perceptron. Same concept, right? As you see in the next few points here in this slide here. So the main thing is there's no change. We still basically do the same thing to train the network. So first of all, you need to present the input patterns as a training set. So a training set of input patterns is presented to the network. So we show the network the set of inputs, what you want the network to learn. The network then computes its output pattern, right? You network here will then calculate the actual output pattern. And if there's an error, or in other words, there's a difference between the actual and the expected, right? Actual and desired output patterns, the weights have to be adjusted. The weights have to be changed, either move up or move down, minimize the error. So there's a minimization of the error involved for it to force the network to learn, right? Make sure it learns. So that's adjusting the weights. Again, same concept as in your perceptron. However, in the back propagation neural network, this learning algorithm, the learning algorithm has two phases, two parts. Two phases. In the first phase, as before, you show the network the input patterns to the show the input pattern to the input layer, the first layer that you interface with the training pattern. the network then propagates, basically move the input pattern from layer to layer until the output pattern is generated by the output layer. So imagine if you are doing something like the XOR or the AND function, you basically move the input patterns layer by layer. You calculate the outputs for each neuron from the first layer, then using that inputs and then you use it to calculate the outputs from the second layer, and so on and so forth until you finally reaches the output layer. And then you do the same thing. You calculate the actual output at the final layer, and then you compare against the desired output and see what's the error. Now, if this output at the output layer is this pattern is different from the desired output, as I said before, the error is calculated. Actually, the error is calculated no matter what, right? The error can then be either small or large. Of course, if it is same from the desired output, then of course the error is smaller. If not, the error is larger. Now, this is where the difference lies now. The difference in your backpropagation algorithm is that compared to the earlier perceptron learning rule, is that the error now is propagated backwards. The error is now moved backwards. That's why the name backpropagation. Move backwards. If you imagine input patterns are on the left, output is over here on the right, I will move the input forward. Again, let's say feed forward, move back forward from left to right until output is calculated at the right hand side, the rightmost side of this slide. Now then you look at the actual pattern outside at this point. How different is it from what you expect, what you wanted, the desired output? Right. Then that error is calculated. Then this error now is moved backwards now, propagated backwards. Back means back towards the left-hand side, right to left. So the input information is propagated forward, left to right. Error is moved right to left. No feedback. It's actually it's not feedback. The signal is not moved backwards. Only the error is moved backwards from right to left. Right? So this error is propagated backwards through the network from output layer to input layer. Same concept, layer by layer. The error is moved from right to left, layer by layer, to the network. From the output to the input layer, the last layer over here, or rather the first layer over here. In the process, right, you don't simply just move it backwards, you move it so that you modify the weights. You modify the weight so that at the end of the day, your error here, the next iteration will be reduced. Or at least you hope it will be reduced. If you use the right what I call values, especially if your network is able to learn. Of course, there's also the other concern, that is, in some cases, your network is not able to learn. And I think recently, my other FIP student actually have some difficulty trying to get his even the deep learning network to learn. Right, so he was doing some work on the recognizing the ripeness of the palm oil fruits. So the first attempt, he just put everything inside, throw the images inside, and then he find that the network was not able to learn. It was giving something like, I think, 20-30% recognition rate, which is very bad, isn't it? Because if you only get 20-30%, I can even tell you, if your network is giving me 20% accuracy, if I throw a coin, it's better than you, isn't it? Throw a coin, it's actually 50% error, 50% chance I'll get it correct. So that is bad. So so the network was not able to learn. So he did something to it. I think he changed the images. I think he actually modified the input data, and then he was able to get about now 95% accuracy in the deep learning. Of course, you need to do other things to tune the network. So that's what I meant. So so it doesn't guarantee that the network will learn. So in some cases, especially the first attempt, you find that if we throw everything inside and assume this is a magic magic box that everything it will learn by on its own. No, it doesn't work that way. You have to sit down and look at it, and then try to modify your network intelligently to make sure it will learn. And then once it does that, the weights are modified as the error is propagated backwards. So as you will see in the next few slides, how the weights are modified and the error will then be moved from right to left. Input pattern is propagated from left to right, which is a forward, and the error is moved from right to left, which is a backward. So you move input signals left to right when you move error right to left, backwards. Okay, this is a figure of what I just said. This is a simple case of three-layered back propagation neural networks. Uh, Actually, okay, never mind. Can see here. So the blue circles represent your neurons, and these are your inputs, and these are the weights to modify the inputs to each of these neuron over here. So this is an M neuron, and this you have a L number of neurons at the output, and you have your M inputs patterns in M inputs. As I said just now, the input signal will be moved from here, this layer to this layer to this layer, and then over here. So output here, you have your desired output, and the actual output is computed from or calculated from your input signals to give you your um, to calculate your actual error. To actually calculate your error of your signal of your network itself. And then the actual error, the desired minus your actual, right? It will then will move backwards to modify these weights. Even can see here I think you can sense the complexity of the calculations, rather and also the amount of work you have to do to calculate. So again, if I ask you to calculate this using pen and paper, I think you, like I said, you will bang sun because it's a lot of work to actually calculate. So that's why we need for this kind of work, we definitely need a computer to help us to do the calculations because it's I think humanly impossible, not to say impossible, that take a long time, and especially when you try to do a system that is needed by industry, right? So it's a lot of things involved. Now maybe I'll move on to this part of it. I think so. Looking at the time, I think we still do it. At this part of it, we try to see how much we can finish. Now we actually looking at it. We will study the back propagation training algorithm, the learning algorithm. How does it work? How does a back propagation learning algorithm works? Same thing as before. Once you have the network set up, right? These guys here, these weights here had to be initialized. They had to set some values for it to get your network to learn. Otherwise, it'll be all zeros. Right? It cannot happen. Right? So that's why I think you might sense it, you might see it. That's why I keep saying that random random number generator is very important in AI work because a lot of time you have to use a random number generator. And then of course, so far I think you may have seen it, you may have sensed it, you may have seen it that you have to be careful with your random number generator. There are some types which is based on the Gaussian distribution, which is a bell curve. Some number generators is based on the bell curve. That means that some numbers have a higher chance of being selected and some numbers have a lower chance of being selected. Then you have the uniform random number generator. That means every single number you want to use, you want to generate has an equal chance of being selected. So clearly, you want to have what? The latter, which is a uniform uh, uniform chance of being selected. Otherwise, you end up with some values keep coming up and some values were not selected so often, which is no good. So have to be careful with that. So you have to set now initialize. You set all the weights and threshold levels of the network to random numbers uniformly distributed inside a small range. So this one even give you a better, clearer guide, clearer equation. That is your random numbers is not just minus 0.5 to 0.5. It is actually based on minus 2.4 divided by f of I, the lower bound. Upper bound is 2.4 divided by f of I. Now, what is f of I? F of I is the total number of inputs of a neuron I in a network. What is the total number? At least for the I think the layer over here. What is the number of inputs you have, right? Actually, it should be the same for all of them because your inputs are all initially will be all be will be connected. Inputs will be connected to all the and the neurons in this layer. Of course, this is based on n number of inputs. This will be n. So it will be hang on. So n inputs in the n. Then you have your this one. Then how about this layer here? You do the same thing. So this will then be treated as your input to the next layer. So in this case, it's only M. This is N for Netherlands, M for Malaysia. So you can see difference here. So the range, the upper lower bound for these weights will be different from the upper lower bound for this. And again, you need to do that for every single layer, neuron by neuron basis. You need to do that for every neuron, every layer on a neuron by neuron basis. Again, even this assignment, assigning the weights to the weights itself will take time. Against that, same as before. What do I get? What do you do? You then activate now. You then once you set the weights are now ready to go. I will now activate the back propagation neural network by applying the inputs over here to the weight and then calculate for each of the neurons here. Same process, right? So let's look at it. You activate the back propagation neural network by applying inputs. So X1 input until N for Netherlands, or New Zealand, for that matter. And then the desired outputs and the output layer, right? The output layer because it cannot be the it cannot be the hidden layer because hidden layer you do not know what's the desired output. Only can you can only calculate that at the final layer, which is output layer. So you then calculate the actual outputs of the neurons in the hidden layer. Now, but you also need to calculate the actual outputs of this layer. What is the actual output so that you can then propagate, move it to it, and then you actually show it to the next layer. So I also need to, even though it's a hidden layer, I still need to calculate this. What is the output of this? So you calculate the actual outputs of neurons in the hidden layer or the middle layer using this formula. Now, if you look at the values of the parts here, the equation inside this square box, inside these square brackets, right? You can see you may be able to see something similar, right, as before. You have a threshold minus theta, and then your weights multiplied by the inputs. So this one, this will be no change, except now you actually advise to use a sigmoid function. Now, for this kind of applications, you normally use a sigmoid. You don't use a hard limiter. Of course, again, in some cases, you may want to use a hard limiter, but in this case, normally for this application, you don't. For many applications, you don't need to use. You do not use the hard limiter or even the sign function, unless you're doing the and or all binary functions. Functions. So you use the sigmoid. We'll come to the sigmoid later on, just to refresh your memory. I think we discussed a little bit about it. Sigmoid, what does it look like? The sigmoid transfer function in the last lecture. Here is the n is your number of inputs of the neuron J. So yeah, so for neuron J, how many inputs are connected to it? So you have to calculate sum of all the inputs, the weighted inputs, the inputs multiplied by the weights. So actually, in this case, your inputs here, though it's not stated, may not necessarily be 1 or 0. So may not necessarily be 1 or 0, especially if you're doing something else, which is not binary. Not binary. So your inputs need not be 1 or 0. Therefore, in such cases, normally you don't use a hard limiter, you use a sigmoid, which is more relevant. Right? You can do it for continuous values, except for if you want to use a network to learn, right? For the binary function. And then once you have this number here, where you calculate this, you then apply these values here to a sigmoid function and see what's the final output based on the sigmoid thresholding or sigmoid activation function over here. So continuing the part B of your activation step, right? You then calculate the outputs of the neuron in output. So finally, you use that and then you move it around. The same thing, you move it and then you calculate also actual output neuron in the output layer. This is a hidden layer, and this one is actually calculated in the output layer, right? Okay, so again, not much difference. Again, it's the same functionality. You have the weighted inputs, the inputs multiplied by the weights, and then you have and then apply to the threshold, and then you apply a sigmoid function to it. Now, this value here, y of k actually is from the hidden from the middle layer. Then you apply this output here to the next layer, which is output layer, right? So again, same here, except that this is n input. This is m number of neurons in the middle layer. Here, this is input I, and here this will be j of k. This is basically this. Looking at this, right? J of k. So from k to j, right? This is jk. This is in middle layer j and input I. Now we have the weight training. We have to train the weights. We have to train the weights. I'm just checking the time because this part here will take a long time to explain. So question is, do we have the time to finish this? I think we cannot finish this because this will take a long time to explain. Huh? So I think I'll stop here on the weight training. We'll come back to this to actually see how we can calculate the weights. Right? So before I stop, before I end the class, are there any questions? Okay. If there are no questions, you all can leave the class and I'll see you back. I think the next one will be the lab on Monday morning. Otherwise, okay, otherwise, you all can leave now. I think David, I think Nathan, I think you want to talk to me. Maybe you can go to the normal Google Meet that we have. Okay, rest of you. I'll be here for a short while in case you have any questions. Otherwise, that's it.
Thanks, sir.
Welcome. Bye-bye. Have a nice weekend. Okay. Final check. Anyone with any questions, comments? If not, that's it. I'll leave shortly. Okay, bye-bye.